We will finish up section 2.1 with the derivative using the definition of a derivative. So what exactly is a derivative function? A derivative function, which we're going to denote f prime of x, of the function f of x, is a function that will give us the instantaneous rate of change, or slope of the tangent line, at any point x in the domain of f of x. So the good news is, if you just watched video 2.1.1, which hopefully you did, if you didn't, go back and watch it, we already found that. F prime of x, or the slope, is when we found the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. Now we used c, but it doesn't change anything. It's the exact same thing. Now, again, this says provided that the derivative exists. We'll talk about times when the derivative does not exist, but essentially what we know is we already know how to find the derivative function. So when we didn't use values like 2 or 3 here, but kept it as c, and for instance, on the last example, we ended up with, I think, 2c was the derivative. And that is the derivative function. So we would say that the derivative of the function, so f prime of x would have been 2x, or f prime of c would be 2c. So we've already done this kind of the longer way, so we'll learn the shorter way in a little bit, but that's exactly what we're going to do again. Now, it's important to understand the different ways that you might see this written. So you're going to see me write it like this a lot of the time. You might also see it as dy over dx, so the derivative of y with respect to x. Again, y prime, which is just the derivative of y, or d over dx, so that's the derivative with respect to x of f of x. So if I asked you to find the derivative using the definition, it's essentially what we just did. So we're going to find the limit as delta x approaches 0 of, and then instead of calling f of c, we can just call it f of x. So this is just f of x plus delta x minus f of x over delta x. So now I'm going to, again, keep writing the limit as delta x approaches 0. F of x plus delta x gives me x plus delta x cubed minus 3, and then minus, x cubed minus 3 over delta x. Now, the hardest part of this question is going to be in determining what is x plus delta x cubed. So I know I can square it pretty easily. I can get x squared plus 2x delta x. Again, why a lot of people choose to use h, because it's less confusing with delta x, plus delta x squared. And then I have to take that times x plus delta x. So it's going to get real ugly for a minute. So it's going to give me x cubed plus 2x squared delta x plus x delta x squared. And then I'm going to take everything times delta x. So x squared delta x plus 2x delta x squared plus delta x cubed. Anything I can reduce out of here, I've got 2x squared delta x and an x squared delta x. Oh, this should be x cubed. So that gives me x cubed, and then I've got plus 3x squared delta x. And these two would add together, so plus 3x delta x squared plus delta x cubed. So that's all of this. X cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed minus 3 minus x cubed plus 3. So minus 3 plus 3, x cubed, all of this over delta x. Don't be the person who forgets that. Keep writing delta x, the limit as delta x approaches 0 until you plug everything in. So now I have 3x squared delta x. You know what? I'm going to save myself a little bit of work. I'm going to go ahead and take a delta x out of everything. So that gives me 3x squared plus 3x delta x plus delta x squared, all over delta x, which will cancel. And now I'm finding the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x squared. Well, as delta x approaches 0, these two are going to both become 0. So that gives me 3x squared. That is the derivative function. So f prime of x is equal to 3x squared. Try doing all of that on your own just to check your math and make sure you know what you're doing before we continue forward. When you're ready, press play to see how you did. Again, f prime of x is going to be the limit as, let's go ahead and use h this time, as h approaches 0 of f of x plus h minus f of x divided by h, which gives me the limit as h approaches 0 of, I'm replacing x with x plus h, so it's 2x plus h quantity squared minus 5, and then minus f of x, so that's 2x squared minus 5 over h. Again, limit as h approaches 0, and yes, this is the kind of work you should be showing. This would be 2x squared. I'm going to do two steps at once here. I'm going to FOIL out x plus h quantity squared and multiply it by 2. So 2x squared, and then I would get 2xh, but times 2 gives me 4xh. And then I would get h squared, but that would give me 2h squared. And then minus 5 minus 2x squared, and then plus 5. Minus 5 plus 5, 2x squared minus 2x squared cancel. Don't forget to write your h. That gives me the limit as h approaches 0 of 4xh plus 2h squared over h. I'm going to factor an h out of everything, so that gives me the limit as h approaches 0. The h is going to cancel, and that gives me 4x plus 2h. But as I plug in 0, that gives me 4x. So f prime of x is equal to 4x. And now they want me to find it at x equal 2. So I'm going to find f prime of 2. So that's 4 times 2, or 8. I want to finish up by talking about times when the derivative does not exist. So we know that there are rules for when a limit exists. The left-hand limit and the right-hand limit need to be the same, and they need to actually match with the value of the function at that point. That's for a limit to exist. We also know how to determine continuity at a point, on a closed interval, on an open interval. Well, in order for a function to be differentiable, what I need is for the function to be continuous, first of all, so I'd need to check those, all of those steps, but I also need for this to be true, which mathematically says the limit as x approaches c from the left of f prime of c is equal to the limit as x approaches c from the right of f prime of c. Essentially what we're saying is the slope from the left has to equal the slope from the right. So thinking about it under that lens, it's pretty easy to see why this function is not differentiable at 2. Because if I look at the slope of the left-hand side, this slope is clearly negative. It's actually -1, but we'll just say f prime of x is going to be -1 because that's a -1 slope. But on the right-hand side, f prime of x is equal to +1. So at the point 2, I've got a -1 on one side and a +1 on the other side. Those aren't equal, and therefore a limit doesn't exist. So whenever you have a sharp turn like that, a sharp turn or a corner, that's where you're not going to be differentiable. You can also look at my second example, or my second non-example, as it were. In this one, you might be saying, well, that doesn't make sense. It seems to be the same from the left and from the right of 0. But if I were going to look at the limit, say, as x approaches 0 of f of x minus f of 0, and this is just this is normal slope formula. This isn't finding the derivative. X minus 0. That would give me f of x, which is, in this case, is actually x to the 1/3. That's the function that I've graphed, the cubed root of x, minus 0 over x. So the limit as x approaches 0 of this. So really what this is the limit as x approaches 0 of 1 over x to the 2/3. Well, if I plug in a 0, or as I get closer and closer to 0, I end up with infinity. So the slope of the tangent line at 0 is infinity, and therefore that's not going to work because it's not differentiable at that point because you can't differentiate infinity. Coming up next, we're going to move on to section 2.2 and take a look at some basic differentiation rules, which you will find a breath of fresh air after what we've just done.